question, but the extrinsic control of the heart is going to come down to effectively hormones, and really talking epinephrine, norepinephrine, which is going to cause that those leaky channels to leak faster. So you're going to see that heart rate really climb and go at a lot higher of a rate. And so on the other side, we've got the vagal tone, which is coming from your vagus nerve, and that's your parasympathetic nervous system through acetylcholine. That is going to cause those gap junctions to leak at a lower level. So it's going to depolarize at a slower rate. So you're going to have naturally a lower heart rate there. Now, outside of that, you're also going to have a little bit of effects of your thyroid hormones. So people that are really hyperthyroid, they can have heart palpitations and really have a high, uncomfortably high resting heart rate. So that's kind of the basics of what's influencing our heart rate. The reason we care more about that epinephrine is because we're going to release that whenever we're doing just stressful training or we're going through stress. So I'm sure all of you guys have been in a car where you thought you were going to get hit by another vehicle, or had something like that really stressful acutely happen, and you're like, wow, my heart rate's going really fast. Or you had to give a speech in front of people. Obviously, some folks deal with test anxiety. All of those are examples of epinephrine being dumped into the bloodstream, which in turn is causing the heart rate to climb, which is great if we're going to go work out. So like if you're an aerobic athlete and you're running a 5K as fast as you can, your heart should be pounding in your chest, because it turns out you need to pump all that blood, all those tissues to keep it going. You're going to have a little bit of the same effect whenever you're doing really heavy weight training, partially because of the psychological stressor of it. And then obviously partially because you have the physiological demands of greater blood flow to your tissues, but it's obviously not the same as the sheer amount of calories you're chewing through whenever you're looking at something like aerobic athletes. So does that kind of explain to you kind of the extrinsic control of the heart?
Yeah, that's good.
So what other questions you guys want to go ahead and review on? So when you're trying to work on learning those steps to an action potential, there's a lot of things you can do to help yourself out. One thing is you can go ahead and put all the steps on flashcards and then jumble them up and then make yourself manually put them through. Writing it out and drawing it out can be a useful way of going through it. Looking at trying to draw just the images and kind of the flow chart of how everything goes together. You can find older examples of me going through it. Also on certain reviews that you can look at. Give me a second because I'm pulling up the old slides. So we can go ahead and talk our way through the basics of contraction. So let me go ahead and share this bad boy. All right. So now we have that initial action potential coming from our brain all the way down through our motor units until we get to those individual nerves, those motor units that are actually going to be firing on the individual muscle fibers. Where one motor neuron is going to innervate tens, hundreds, even thousands of individual fibers. Now, eventually that signal, that action potential, is going to get all the way down to the end of this axon terminal, which is on the muscle fiber. We're talking about where we have what's known as the neuromuscular junction. Now, these axons in turn are going to release vesicles. So they're little storage packets of acetylcholine, and they're going to be released into the neuromuscular junction. This acetylcholine is going to go across the neuromuscular junction, and it's going to bind to what's known as the ligand-gated receptors. This is going to allow sodium to go into the sarcoplasm, which is going to be bringing up that membrane potential until we hit that threshold. Then it's going to open what's known as the voltage-gated channels, and then when those open, sodium is going to rush in even faster, and now we have an action potential. This action potential is now going to travel down the sarcolemma in all directions from this neuromuscular junction. That's just the cell membrane of the muscle. From there, it's going to go into what's known as the T-tubules, which is where it's going to be able to then propagate from the T-tubules, because they're little, essentially, holes that go through your muscle fiber, so this action potential can travel at a faster rate. It's going to cause your sarcoplastic reticulum, your SR, to release calcium from calsequestrin into the sarcoplasm, the cytosol of your muscle cell. This calcium is then going to go and bind to troponin. Once it binds to troponin, troponin itself is going to move tropomyosin, which is the blue bands, of proteins from covering the active binding sites on actin. And once they're uncovered, now myosin can grab hold of actin. From there, it's going to ratchet forward. ATP is going to come in, so it's going to release from actin. It's going to hydrolyze to get it to spring back, and then it'll go ahead and grab and pull forward again and keep doing so as long as ATP is available to get it to unlink and calcium is available, so those binding sites are going to be active on those muscles. So it's okay to be a little confused. It's okay to obviously struggle with this stuff. It's a lot going on. The key, part of this is not just repetition, but thinking it through while you're doing it, and what are going to be the ways where you've learned anything where it's stuck. Because obviously, you know how to tie your shoes. You know how to, get ready. So you know how to do a multi-step process. This is the same thing, but you got to figure out what's the method for you to remember this multi-step process. Does that make sense?
Yes, it does. I'm going to go back and rewatch this a few times. And
that's okay.
Hopefully I can
just watch it. Like I said, try to draw it out on a piece of paper. So try to draw your own motor neuron, try to draw your own neuromuscular junction, draw the sarcolemma, draw into the T tubules, draw every little piece of it. So you can kind of understand how you go from literally, you can see how it's sublettered A to B to C to obviously myosin pulling actin in on both sides we have in the bottom right image. So you got to keep in mind, the methods that you guys have used for studying has gotten you to where you're at, which means there are certain classes that you're probably doing very well at, meaning your study methods there are perfect. Do not change them. You are getting the grades you want. But there are other classes that you're not getting the grades you want, or you're not retaining the information in certain ways that you'd like to, which means the methods you're using don't work. So now you got to try something different. And that's a hard thing for a lot of people to grapple with, because the techniques that get you to certain levels don't necessarily get you to the next level. What other questions can I help you guys with? When it comes to blood flow distribution, we've got two separate graphs here. Graph on the left is looking at, notice, percentage of your blood output. Graph on your right is looking at total volume of blood output. So notice as we go from rest to light to moderate to maximal exercise, we're obviously having huge gains in our cardiac output. Now, as far as percentage of blood flow, notice the amount going to your kidney, liver, stomach, intestines is really shooting down. Going to your skin is peaking somewhere around light, getting into moderate, and then actually going down again when it comes to percentage. Where we come over here, notice we have the highest blood flow to our skin at moderate, which is actually important. That's why it's really easy to overheat when you're exercising maximally, okay? Now, notice muscle is getting a massive increase in both percentage of cardiac output and then obviously the total volume. Meanwhile, notice the heart has the exact same percentage, but it's going to have a slowly ticking up total volume because the heart needs to stay oxygenated. So it's always going to use 5% of its own output to maintain its own aerobic performance. And then finally, your brain is consistently getting a lower percentage, but notice it's getting the exact same absolute blood flow, whether we're at rest or at maximal exercise. Turns out we don't want to try to starve our brain of oxygen. That's a bad choice or a real bad decision of things to do. So does that kind of help you understand a little bit of how that blood flow distribution is going once we're getting into exercise, and then how it's going to ramp up and ramp down to certain tissues? Cool. What was the second part of your question? Because I think I only answered half of it.
Yeah, you're good. It was about like cardiac output and like stroke volume in like people who are training, or like even just like normal people, I guess.
Yeah, no, I mean,
like the changes in between the two.
Yeah, no worries. So actually, it's kind of funny because this is where we're going further into the class and really kind of digging in to what's going on. So it turns out, as our exercise intensity goes up, our heart rate's going to go up, and it's usually a straight line. And this is going to be the basics of where we're going to do sub-max testing in one of the later labs. You're just going to walk on a treadmill and get your heart rate at different intensities. But stroke volume is actually going to go up and then peak usually around, notice we say here 40 to 60% of your VO2 max. Figure for a lot of you guys, it's going to be probably around like 120 beats per minute. Might be higher if you're in really good aerobic shape. That's why we can use submax exercise as an indicator of your maximal heart rate, because we figure stroke volume isn't also going up. Now, the stroke volume of someone that's in really good aerobic shape, okay, just about everybody's stroke volume from being at rest, so notice it's somewhere between 60 to 70 milliliters to at max, it's just under 120, it's gonna get close to about doubling from rest to maximal exercise. People that are in bad condition, people that are sedentary, out of shape, their stroke volume max, so that's them going 100% or at least at a really high exercise intensity, is typically only the same as an elite level athlete's stroke volume at rest. So your stroke volume improves with training. Your maximal heart rate doesn't really change with training. It might actually go down a little bit if we're really increasing that stroke volume and your heart size. So the big part of cardiac output that we kind of have control of, and remember that's just the heart, so it's only one of the three components of our aerobic system, is going to come mostly from changes in your stroke volume. Does that kind of clear up, or at least explain a little bit more of your second part of your question?
Yeah, thank you.
Hey, no worries.